So, Kepler. Johannes, right? Johannes Kepler. Anybody know the history? I think his first name was Johannes. I'm trying to think of Kepler's first name. No? All right. Well, Kepler came up with 3 laws. Kepler's 3 laws are very different than Newton's 3 laws. Now, Kepler also had some ideas that Newton later proved to be, they're on the right track, but they're not exactly right. And Newton proved that with a lot of his laws later on. So you might be wondering at the moment, like, why we're doing this after we just looked at Newton. The concept of gravity, though, affected Kepler's work. So we learned the idea of gravity first, so it's sequential in our minds, so we understand the ideas. Kepler came up with these 3 laws, and he specifically called them the laws of planetary motion. We're going to validate some of those laws, especially the 3rd one, and then we're going to talk about satellites and talk about orbital velocity. So let's jump right into this with Kepler's first law. And Kepler's first law, I think you learn in like 4th grade. You learn it when you make a planetarium or a solar system model. It's like a classic 3rd, 4th grade project. You get like a shoebox or something. You make a model of what the solar system looks like. And every student does it wrong. And nobody realizes when they're that young. Because they make these wild ellipses, right, like this. And that's true for Pluto. But most planets' orbits are very close to circles. Look at the eccentricity of the ellipse for Earth. This is not a circle. It looks like a circle. It looks perfectly to be a circle according to this, but it's not. Mars, slightly more eccentric. E stands for eccentricity, by the way. The higher E is, the more it is closer to an ellipse than it is a circle. A circle's eccentricity is what value? Using common sense here?
0.
0, very good. A circle's eccentricity is 0. Someone who's eccentric, right? Think about a person who's eccentric. Think about, yes, Carolyn, you're very eccentric. A person who is eccentric might be a person who deviates from the norm in certain areas. Well, an ellipse deviates slightly from the circular shape it has, which is why it's called its eccentricity. It's how much the circle is getting kind of flattened and stretched. So the more flat and stretched the circle is, it becomes more of an ellipse, and the more it becomes an ellipse, the more eccentric its rating is. Now, the key I want to point out, though, again, is that most planets, though, although following an elliptical orbit, their orbits are really, really close to being circular. Okay, really close to being circular. The focal points are important. Have you heard of the phrase focal points for ellipses yet? Have you used that phrase at some point in time? Okay, if you haven't, some of you are nodding yes, some are like looking lost, so I'll point it out. So a focal point is a location in an ellipse that is not the center, but it kind of acts like a center. For example, if I were looking at Pluto, one of its focal points is probably around here, and that's the sun. And the other focal point is just a point in space. I'm barely drawing it there for Pluto. Now, for the Earth, though, the sun is practically here. And the other focal point is pretty much right next to it. It's not exactly lined up, but it's so close that these 2 focal points are practically on top of each other. Mars is in between the 2. Okay, Mars's first focal point might be like right here. And the second focal point for Mars would be like right there. So what we notice is that the focal points get further and further apart as the ellipse becomes more and more eccentric. So again, a circle's eccentricity of 0 simply means the focal points are literally on top of each other. One is on top of the other. They line up perfectly, as opposed to what we see with Mars and with Pluto. Okay? As opposed to Mars and Pluto. All right, let's continue. That's Kepler's first law. By the way, Kepler's law is one of the positives of this section. Not heavily math we're going to work on. A good amount of conceptual. So to give you a little breather from the heavy math stuff, we will still do a math problem or 2 involved here, but light math, and you'll see that. Okay, Kepler's second law, also conceptual. Kepler's second law. Here's what his law says. Equal amounts of area are swept out in equal time intervals. So what does this mean? This means that each of the regions that you're seeing in this diagram on the left has the same area. And the line that is doing the sweeping out is the line between the planet and the actual celestial body it's orbiting. In this case, the sun. So, for example, the moon around the Earth follows the same law. The Earth becomes the center, and this becomes the moon now. And the line drawn from the orbiting body to the central body is the line that we're talking about. So you'll notice that these pieces of pie, right, pizza pie, they look skewed, they look different. It's because the sun is not in the center. And this is really extreme over here on the right. Right? You can clearly see this being very extreme on the right side. And that's showing something like, a much more exaggerated orbital shape versus an actual orbital shape. So what can we conclude from this? Can anybody make a deduction from this? What information can we gain from Kepler's second law? Because there's something we want to draw from this information. This is not the only thing. Now, yeah, this is true. Same time period, same areas. But what can we gain from that information, Jack? What do you think?
Is the speed going to be different?
Very good, Jack. The speed's got to be different, right? Think about it logically. Let's go through this. Every single section of this piece of pie is how much time? Use common sense. Figure it out. But exactly, what is the time, though? You can figure it out.
Each piece a month?
A month. There's 12 pieces, right? And it's the Earth around the sun. So they're around, I know every month is not the same. Trust me, I know that. But we assume that every month for the sake of this is the same. Each of these pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Each piece is a month. Each piece is 1 month. So as a result, if we're traveling for a month, and look at the distance traveled in each month. From month 5 to month 6, this is a pretty short distance, isn't it? But look at the month 10 to 11. Isn't that much longer distance? So if you're traveling the same distance in the same time period, then what we're going to know is that it's got to speed up or slow down. So each month as we go through this, we're going to see that the speed of the planet changes. So what can we conclude? When it is closer to the sun, what happens? When it is closer to the sun, just looking at the distances traveled, yeah? Yes, gravity gets increased when you're closer to the sun. But what was the other part that we want to conclude? So therefore?
You take longer to orbit in the same amount of time.
You go a longer distance in the same amount of time. Agreed. So from that, so the speed increases. Again, from month 10 to month 11, you have the same time period as month 3 to month 4, but look at the distance traveled along this path. That is much greater than the distance traveled along this earlier path up here. Right, look at that distance, look at the two, far different. So what we can conclude is that V, and let's call this V1 over here, and we'll call this V2 over here, V1 must be greater than V2. V1 must be greater than V2. And that's also common sense because gravity is stronger when you're closer, so you're probably going to get a faster speed as a result as you're orbiting. Okay? So V1 is greater than V2. Not that much, by the way, especially with the Earth. We're really not speeding up that much. And that's, again, because our orbit is relatively circular. But if you're Pluto, Pluto really slows down significantly. It really does. And this exaggerated orbit on the right here shows it a lot better. Okay, because think about those distances comparatively. This gap over here, I mean, look at this distance right there in red compared to the distance in blue. Significantly different, right? So Pluto, when it's at the far extents of the Milky Way, I think Pluto actually, or Neptune, I forget which one, or Uranus, one of them exits the galaxy and comes back in. Technically, I think it actually exits the Milky Way. Am I right? That's the solar system? There's something about one of the planets that its elliptical orbit takes it out of what we considered part of the solar system for a long time, which is probably the argument about why one of them was a moon, wasn't a moon, or was a planet. Point being, when it's further away, it's going to go far slower. It's going to speed up as it gets closer. Let's take a look at Kepler's third. Any questions on the first and second law? Yeah?
Wait, so is the second law then not true because it's not covering equal areas in equal amount of time?
So the second law tells us that it is covering equal areas in equal amounts of time. The thing is this, though, Mauro. For the Earth, it's barely noticeable because our orbit is pretty much circular. So it turns out for the Earth that even this is an exaggeration. You follow what I'm saying? So in reality, the difference in velocity is not very great for a planet that is relatively close to a circular orbit. As it becomes more eccentric, then that velocity difference is more distinguishable. Okay? Or more exaggerated. Let's take a look at the third law. The third law is the one that involves a little bit of math. So let's take a look at what it says. The third law says the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. And that is a pretty wordy thing to say, right? So let's write it out. The ratio, so I think of ratio as fraction, of the squares of the periods. So let's write that out. The squares of the periods. So let's say we'll call this planet 1, we'll square its period, and planet 2, and we'll square its period. The ratio of the squares of the periods of any two planets is equal to, the ratio of the cubes of their average distances from the sun. So we're going to say R1 cubed over R2 cubed. And what we're going to recognize for a problem like this, is that we can resolve this by switching these two positions. Remember mathematically earlier this year I kept saying, whenever you have a proportion, you can multiply this up and divide that down. So just switch these two positions. And what will that yield? That will yield T1 squared over R1 cubed equal to T2 squared over R2 cubed. And that's what this law really is right here. Although stated verbally, the verbal representation becomes this. But the one that's actually important is circled in blue. That's what this law says. And this says that for any planet, this theory is true. So if we look at Pluto versus the Earth, and we actually take into account the values, we'll get the same ratio. It'll come out to be the same number. And there's the number right there with Earth and Mars. Here it is, right here. And again, there are going to be slight differences. That's going to happen. In addition to this, again, like I mentioned, Kepler's laws, although being mainly true, are slightly off. And again, that's because of the fact that other bodies cause gravitational pull. If the sun were the only thing causing a pull on all the planets, then these numbers would be identical. Absolutely identical. But you know what? As the Earth goes by Mars, it kind of pulls on Mars a little bit. And Mars pulls on the Earth too. And as asteroids come through the solar system, as the moon goes around the Earth, it affects the Earth. Those asteroids affect planets. So the values of this data would only be exact if the sun were the only mass, and everything else had no mass, technically. And it was just being revolved. Now, if there was no mass to anything else, it wouldn't exist. So it's like which came first, the chicken or the egg. You can't really say that. So the idea, though, here is that, again, we know that these ratios are practically the same quantity, T squared over R cubed, for any given planet. Now, these values are given with units of seconds for time and meters for distance. And that's nice, don't get me wrong, but when we start looking at astronomical values, we use different units. So let's take a look at the same page or the next slide to see the values that we end up using actually. So for periods of planets, we don't use seconds. It just doesn't make sense. Seconds are such a great value. So what we use is Earth years as a baseline. So what is the period of revolution of the Earth? Well, it's 1 year. Because after 1 year, what do? We go all the way around the sun. which is why you hear the saying, how many trips around the sun? Right? Trips around the sun means years. Somebody says, oh, you made another trip around the sun this year, it means it's your birthday. You went through another year of your life. So one trip around the sun is one Earth year. But you know what? Pluto takes 248 years to go around the sun. 248, which is incredible to think about that. We have to literally spend 248 times going around the sun, and it goes around once in that whole entire period. So everything on this scale is a function of Earth years. Mercury, look at Mercury. All the way in there, right? First planet. My very educated mother just served us 9 pizzas. Is that what you guys did? Or eccentric mother? Anybody have an acronym that was different from that? Something like that, right? That's how you remember what planets are what? Anyway, innermost planet, shortest period length. Outermost, largest. What else do you notice? Distance. Obviously, is the innermost. What does AU stand for? Not AU. Look up. AU. George, yeah.
Atomic unit.
Not atomic unit. Good guess, though. Think about it, George. Is the Earth one atomic unit from the sun? An atomic unit would be the unit of an atom, right? If you're close, a non-atomic unit.
Astronomical unit?
Astronomical unit. Very good. Astronomical unit. So, astronomical units are measured in Earth length. Earth to sun lengths. So the Earth's astronomical unit distance is 1. So we're very egocentric, right? Humans as a culture, whatever. I'm not saying you are. We as a culture are. We care about ourselves, which is important because other species honestly don't matter as much. Terrible to say, but it is the truth. We don't want to kill other species. I'm not encouraging that at all. But anyway, my point is, everything is about the Earth. So look, all the numbers are related to Earth. Same here. So instead of calling this meters or kilometers, we say, let's define the length between the Earth and the Sun as 1. And we're going to come up with this made-up unit, and we're going to call it AU, an astronomical unit. The distance between the Earth and the Sun. And everything else is a factor or multiple of that quantity. So Pluto is about 40 times as far as we are on average. On average. Because again, what did I say Pluto does? Pluto has a very, very eccentric orbit. So sometimes Pluto is really close to the Sun, and other times it's really far. So on average, Pluto is 40 times further than we are. Around 40. Neptune, around 30 times further. Uranus, about 20 times. Saturn, around 10 times further. And it's just a coincidence that these happen to be numbers that are around like 10, 20, 30, 40, okay? And the one before it 5, it actually works out nicely. So if we calculate t squared over r cubed for every single planet, those are the numbers that we'll get. Again, just reiterating the point that this is a relative constant. I know they're slightly different, right? We see some changes here, but for the most part, it's relatively constant. Okay, again, the things that vary it are the gravitational pull from the other planets that are going or passing it in its orbit. So how might you be asked a question on this Kepler's law, or the third law, because this is the one that could involve math? Maybe you're given the information about, Mercury, you're given the period of Mercury, and you're given the period of Jupiter and the distance from Jupiter. You have to find out the distance of Mercury. Well, the concept is that t squared over r cubed is the same for all things. So we'll get to an example of that in a couple slides. Yeah, in a couple slides we'll get to an example of where we'll see that play a role. But the idea I want you guys to recognize is that for any planet setup, you could always do this. T squared over r cubed equals whatever constant is on the other side. Okay, that's always going to equal a constant on the other side. I ran out of space there, sorry. My screen is much shorter. My screen ends here, by the way. I don't know why it extends over here, so whenever I'm writing, trying to squeeze things, you're like, why is it doing that? It's just the way it's set up and this thing swaps. All right, so let's take a look at Kepler's third law and prove it. Okay, let's prove it using Newton's law of gravity. So we're going to start by assuming we're going to call M1 in this problem the planet's mass, and M2 the sun's mass. Okay, the planet's mass is M1, the sun's mass is M2. Start by recognizing first, in circular motion. By the way, the assumption right now is that we're looking at a circular orbit. I know they're elliptical, but we have to assume they're circular for this to hold true. In circular motion, what is our governing equation of forces? Fc equals FC equals from sections 5.1 to 5.3, George?
MV squared over
MV squared over R. So let's start with that statement. What is the M? Is the M the mass of the thing that's going around in a circle or the thing that's in the center? What is M in this case? The thing going around in a circle or the thing that's in the center of the circle? Christina? The thing that's going around the circle. And think back, when we spun the rubber stopper, the mass was the thing that was spinning, right? Not the center of it. It was the thing that was spinning itself. So that's the thing that's moving. What's moving here? The sun or the planet? We should all answer that right away. What's moving? The sun or the planet? Okay, the planet. Now, technically, the sun is also moving, but that's a whole other story. With regards to the planet itself is moving. Okay. So that's our formula for circular motion. What causes circular motion that keeps planets in orbit? What force keeps planets in orbit specifically? Gravity. So we could say that gravity is G m1 m2 over r squared. Since the centripetal force is provided by gravity, these equations are equal to one another. So I could say m1 v squared over r equals g m1 m2 over r squared. Next, cancel m1 on both sides. Reduce the r's. Let's drop this one off on the left side and get rid of the square on the right side. If you didn't know you could do that, it's good to know. Write yourself a note. Just because things cancel on the top doesn't mean they just can't cancel on the bottom. They also cancel on the bottom. But we're left with one r over here, and this r is gone on the left now. So what does that give us as an equation? It just says v squared equals g m2 over r. Well, why is this important? Here's why it's important. What we can do next is this. We can say to ourselves, how do we find the average speed of something going in circular motion? What have we been replacing it with? We want to find the average speed of something in circular motion, and we didn't know the number. How do we find the average speed of something that's going in a circle? What do we do, Jack? Close. We're not looking at frequency right now. If I want a definition for average speed, we don't have frequency. It's not given in this problem. Use period instead, is what I'm saying.
2 pi r over period.
Good. 2 pi r over time. Remember from earlier on in these lessons, we said that the speed is 2 pi r, which is circumference over time. Or we said that the speed was 2 pi r times f. I was telling Jack we should use this upper formula here. So let's take that formula and plug it in for v. So I'm replacing v with 2 pi r over the time. This is, remember, distance, circumference, over time. And if we're trying to prove Kepler's third, we probably want to get t squared and r cubed somehow there. So let's go ahead and distribute the square. So far, so good. And Kepler's third told us that t squared divided by r cubed is a constant. Agreed? That's what Kepler's third law said. So let's get t squared over r cubed somehow. So I need to get rid of this t squared in the bottom and move it where? Top. So let's move the t squared up here. And let's move this r squared where? Down here. And then let's take the g and m2 and move it where? So let's just move things diagonally is what I'm saying. Move things diagonally until you get t squared over r cubed by itself. So again, I'm going to move this guy, I'm going to move this guy, and I'm going to move this guy. All three of the things that I circled, I'm going to move them all diagonally. And that will yield the result we want. If I move t squared, it'll put it up here. If I move r squared, that'll make this r cubed down here. So again, t squared is going up over here. R squared is coming down over here. Then GM2 is going in the denominator down here. And 4 pi squared remains up top. So why is this important right here? How is that proof that Kepler's third law is valid? How is that proof that Kepler's third law is valid? We've got t squared over r cubed. That's what we were looking for, right? And what did Kepler's third law say? It said that t squared over r cubed is a constant for all planets, right? What's 4? It's a constant. What's pi? What am I getting at? Obviously, everything here is a. M2 was what? What was M2? The sun's mass. A constant. What's G? The universal gravitational constant. So the point is that t squared over r cubed, it turns out it's this formula. Well, this number here is really just number 1 in terms of astronomical units and years. Or it's that other number we had a couple slides back. What was that number? 2.9 times 10 to the negative 19 if I'm looking at seconds squared per cubic meters. Whatever. It doesn't matter what the number is. The fact or the point is that this ratio is a constant. So t squared over r cubed must also be a constant, which is why this is the same quantity for all planets. It is constant. The key, again, is that we assume the orbit is practically a circle. Because if it weren't a circle, take a look, this would be gone right here. We cannot use that formula if it was not a circle. Because this is the formula for circular motion. Circular motion. So proof that Kepler's third law is a constant. I'm not going to ask you to prove it on a test, I'll tell you that right now. But it's possible next year in AP, you could be asked something like that on an AP exam. So good to know that it does prove it's a constant. You guys would most likely have to be able to use this fact. Okay, use this fact. And say, again, like if I gave you 2 of them, if I gave you Neptune's period and average distance from the sun, right, for Neptune, for both of these, and then maybe you had the average distance from the sun for Jupiter, you could find the period for Jupiter as a result by setting t squared over r cubed equal to t squared over r cubed for any 2 given planets. Okay, for any 2 given planets. All right, with that said, I want to get into the last part of today's lesson. Nice, we're doing well on timing. Let's talk quickly about what satellites are. What satellites are. So we know of satellites as those things that help us use our cell phones. Pretty much what we know of satellites as. Satellites are not just that. Those are man-made satellites. Satellites are any celestial bodies that orbit a central body. So the moon is a satellite of the Earth. The Earth is a satellite of the sun. We call it planets, and that has to do with, you'll read in your book actually, I think the book goes into this. Planet has to do with the word like, it's an older, I think, Greek word that really meant like wandering. Planets wandered through the sky was the idea, so they called them planets. But they're really just satellites. We are all planets that we're on, where Earth is a satellite of the sun. So anything that orbits another central body is indeed a satellite. Okay, is indeed a satellite. Let's take a look more specifically about satellites, not just what it is. So how do satellites stay in orbit? How do they stay in orbit? So you see a diagram on here. For every 8,000 meters long horizon, the Earth curves downward by 5 meters. Isn't that crazy? That's why for a long time, what do people think?
It's flat.
Yeah. And I would, if it were me and I weren't a scientific person and we're in the 1500s, I might believe that person. Like, yeah, you know what? It is flat. Because we're looking at the horizon, I see a flat line. If you look at the horizon on a big enough expanse, you kind of see some curvature, but for the most part, you see a flat line. And if you keep walking toward the horizon, it seems like you're walking flat, right? And it seems like you never get there, because the horizon just keeps moving further from you. That's the whole idea. You are seeing the curvature of the Earth by seeing the horizon ahead of you. The curvature is so light. 8,000 meters you walk this way, you only drop 5 meters. So, this concept, the Earth's curvature, in pre-calc, have you talked about concavity at all? Concavity, concave up, concave down, no? Right. So in this case, the curvature of the Earth is so slight that satellites don't have to do too much to stay in orbit. All they got to do is this. Every 8,000 meters that a satellite goes this way, they got to make sure they don't fall more than 5 meters. That's what a satellite has to do. It has to move around the Earth with the exact same curvature that the Earth has. So here's what a satellite really is. A satellite is an object that's freely falling. It's freely falling, actually. But it's got initial horizontal velocity. Remember earlier in the year, we shot the marble out and dropped the marble at the same time, and one went like this and one fell. They both hit the ground at the exact same moment. That's the same concept, but you know what? If we fired that missile or that bullet or that projectile fast enough, it would become a satellite. That's called satellite's velocity or orbital velocity. There's also a thing called escape velocity. If a rocket that's going to become a satellite is fired with too much velocity, it gets out of circular motion around the Earth and it'll go out into space, tangent to the curve. But if it's the exact right velocity, which it always is, because we're scientists and we make sure of that, the satellite will stay perfectly in orbit at that exact height or elevation. At that exact height. So a satellite is really an object that is freely falling toward the Earth, but watch, here's the Earth's surface. It's falling, but it's falling perfectly in line with the Earth's surface. So if it's always falling with the same exact curvature of the Earth, it's never going to hit the Earth. It's always going to go around the Earth, and it's going to keep doing this because it's constantly falling with the same curvature. If the velocity is slightly lower than it should be, it will eventually careen into the Earth, crashing into it. If it is slightly too large, it will go off into space, tangent to the curve. Okay? So the idea is that orbital velocity has to be a very, very precise value. Let's talk about that orbital velocity and what that value has to be. This is a much quicker derivation. It's the same starting point as last time. m1 squared over r equals g m1 m2 over r squared. It's the exact same starting point we had for the derivation of Kepler's third. Again, canceling the outer mass, because it's on both sides, right? In this case, the satellite. I'm calling the outer one satellite, the inner one central object now, instead of the Earth and the Sun, so we could just generalize more. And then I'm going to cancel r, and cancel one of the r's over here. And I'll get v equals g m2 over r, all under the square root. That's the orbital velocity needed to keep a satellite in motion above the Earth. Write yourself a note, please, that m2 is the central object. m2 is the central object. So what is a satellite's velocity, speed, a function of? And what is it not a function of? More.
It's a function of its own mass, not the mass of the satellite. The central object.
So it is a function. Say it one more time, Laura. Make it clear.
It's a function of the satellite's mass, the central object's mass.
Good. Okay, better. So it doesn't matter how big the satellite is. If it's a tiny satellite, that's a baseball. If it's a huge satellite that actually transmits signals, whatever it is that's orbiting around the planet, its mass doesn't matter. M1 canceled. The mass of the satellite canceled. So what matters in the end? As Maura said, the central object's mass. What else matters? What else matters, George?
The distance between the two masses.
The distance between the two masses centers. So we have to make that clear, because if this is the Earth and this is a satellite around it, the distance that we're going to refer to is from here to here. So we have the Earth's radius plus the gap between the satellite and the Earth plus the radius of the satellite. We will finish this off in class on Thursday before we start an activity. There is one example. If you want to give it a shot, you can. If you want to get a head start in the homework, you can do that as well. But I want to get into this one example next class. Have a good day, guys.